The third chapter in my inorganic chemistry series is called Point Group Theory, and it deals with symmetry of molecules, which is useful for spectroscopy, polarity, chirality, and a number of other things. And it can be highly mathematical. In fact, there are entire graduate courses covering point group theory or group theory. But this is just an undergrad course, and we're going to scratch on the surface, and we're going to make it more three-dimensional and visualization based rather than mathematical, although there will be some small mathematical aspects of that. You already used symmetry for Gen Chem when we looked at Vesper theory, and the symmetry, you've related it of a molecule to polarity, or you've used it in organic chemistry to determine if a molecule is chiral or achiral, or also for spectroscopy. You probably have done your share of NMR and looked at something like this here. I'm going to allow this organic molecule into my inorganic lecture just this one time. But you know very well that you expect three different signals here because there's symmetry, right? There's this group is equivalent to this group, so you would expect one signal for all 6 of those hydrogens, and the reason you argued is you have free rotation here, so all 3 are equivalent. And then we have these 2 groups here, and then this one would be the third signal. And you also argued that these 2 here are equivalent, and so there's another, if you put there's symmetry that dissects all of those carbons. It's a little harder to draw, but there's a plane that dissects this molecule here, which makes these 2 groups equivalent, right? And so then here simply we have 2 groups that are equivalent, and this one is on the plane. But again, you argued that, okay, there's very fast rotation, which is faster than the NMR time scale, so your NMR can't distinguish between those groups. But the point is that you have used symmetry, you have already an understanding of it, and so now we're going to get a little bit more detailed. And so I highly recommend that if you have a model set, nothing beats building and looking at a molecule in 3 dimensions to find the symmetry elements, which are planes and inversion centers. And then we'll go through every single one of those here in a second. And again, it's used to determine whether a molecule is polar or chiral, and then it's heavily used in spectroscopy. And we're going to look at iron Raman. We're going to be calculating the number of iron Raman bands, and don't worry, it's not too complicated. 2 of the resources that I can highly recommend is SimOtter of the Otterbein University. Has a nice tool out there for simulations. I'll go there in a second just to show you. And then ChemTube 3D, you can actually take a molecule and it will tell you the symmetry, and it'll try to let you play around with it. So let me go to that real quick. So here's the Otterbein simotter.org website. You want to go to symmetry, and then later on this will make more sense to you, but if you click on any of these, it'll come up with a 3-dimensional, well, it's flat, it's a monitor, right? But you can rotate it and look at it. And then on the right you have, you know, this one has an inversion center. If you click on it, this is a little goofy, but you click on the little box, it shows you where the inversion center is. And so we'll come back to that in a second. And also this site's quite useful. It's got tons and tons of different molecules you can look up. Dichlorobenzene, and it tells you the point group here. It's got a C2V. This will make more sense later on. So let me go back to the lecture here. Okay, so you've used mirror planes already, so we're going to go through all of these symmetry operations or symmetry elements. And so a symmetry element is either an axis or a point. And if you move your molecule through this axis or this point, it becomes indistinguishable from the shape or molecule that you had prior to obtaining the operation. So this right here is not a symmetry operation because your molecule ends up in a completely different position. So this would be something that's internal. I just want to show you this because you probably use that to determine if something is chiral or not. And so it's pretty easy for you. You have a carbon center with 4 different groups. You know it's chiral. You don't have to visualize that. But it is kind of nice. So here I have, just got to find it right. So here I have, I don't know if you can hopefully see the orange and the purple. And so then if you try to superimpose them, you'll find that that doesn't work no matter what you do. So if you've determined that this is chiral. And so this molecule doesn't have any internal mirror planes. So internal mirror planes is if you projected one of these planes inside of the molecule here, right? So this is flat. If you put a mirror plane here, this part will be fine. But these two are going to exchange, so the hydrogen and the iodide would exchange, and so there would not be a mirror plane, an internal mirror plane here. So, but mirror planes are the first one that I want to talk to you in detail. Right? So here we have a molecule. It's flat. Anything is flat, it's going to have a mirror plane, a sigma. We call those sigmas. And so in the plane of the molecule, you will have a mirror plane, but you also have one that dissects that carbonyl bond here. So these are outside of the mirror, and so it projects through the mirror into itself. So in order for there to be a mirror plane, these two atoms have to be the same. If this was a fluorine, you would still have one mirror plane, but only the one in the plane of the board, and this one here would no longer be a sigma. Okay? So another way to look at it is simply if you can cut a shape or a molecule into 2 identical pieces, just like this trigonal prism here, which you cut in half, you end up with 2 identical pieces, then that means there is a mirror plane or a sigma here. Of course, there are several different ways to cut this molecule into 2 halves. If you looked at it from the trigonal base, you could cut it here, you could cut it here, and you could cut it here. So there's 3 mirror planes here, and then there's the one in the center that's indicated here. So we have at least 4 mirror planes. And so I do encourage you to play around with that and find that yourself. And as I go through some of these molecules and I ask you, hey, here's this molecule, is there a C2 or is there a mirror plane? Then you might want to pause and figure this out yourself before you finish looking at my lecture, because that's the only way you can learn it. And pause it, build the molecule, find it, and go at your own pace. That's the beauty of online. You can just do this at your own pace. And then continue the video and let me explain, or try to explain. And sometimes I'll hold up my molecules and I'll try to show you, look here, you can rotate that 90 degrees or 120. All right, so here's another way, and we've already discussed that you can cut it this way. It would make 2 even pieces. Not that difficult to realize, and these are just 3 other pictures of very symmetrical shapes, and you should probably play around and see, can you find any more mirror planes? These are highly symmetrical, so we already know we have 4 here, but this one might here. This box might even have more than that, right? So play around with that on your own. It really will be helpful, and it can be a lot of fun to look for symmetry elements. So, but before we look into more detail, and we're going to come back to these sigmas. The mirror planes are either vertical or horizontal, and they have to be with respect to something, right? Because we know that these molecules in 3 dimensions, they don't really have an axis. These are assigned, and so in order to assign an axis, we need an axis of rotation. We call that the highest axis of rotation is called the principal axis. So you must have that one before you can assign a mirror plane that's horizontal or vertical. So we'll come back to these mirror planes. So an axis of rotation, we call them N. C1 would be a 360 degree rotation. C2, as I have listed over here, 3, 4, 180 degrees, 2-fold. And so you can say that N is going to be equal to 360 degrees divided by that rotation. So if you have if you rotate a molecule by 120 degrees, so 360 divided by 100 would be N equal to 3. So a 3-fold axis here would be this. In other words, you have to, if you do this 3 times, you get back to its original location here, right? If we label this hydrogen 1, 2, and 3, So you have to do 3 C3s in order to get back to the original position where the hydrogen 1 would be back into itself. And also, by the way, symmetry element E, which I have a separate slide for, is a 360-degree rotation, or a C1. We call that an identity. This is a symmetry element meant that every shape, every molecule, everything out there has a C1. You can rotate anything, no matter how achiral or asymmetrical it is, and get it back into itself. So let's take a look at a few molecules here. Wait, a light. Let's take a look at this molecule here. It's water, right? We know H2O. We know it's bent, and there, if you put an axis through the center, this would be a C2 if you rotate that by 180 degrees. And then now we have these mirrors, and so if we would have this as the principal axis. There are no other axes. Some molecules that are more symmetrical have other axes. They have, for example, you can have a C6, benzene will have a C6, but it'll also have C2s and C3s. So the principal axis is the one that has the highest order, the one with the highest number, C6, and then all of those mirror planes are either vertical or horizontal with respect to that principal axis. So if this is the principal axis, and I put it up from top to bottom, instead of on the side, right? I can put water, I can draw it like this, and then my C2 would be here, and so my mirror planes would be here and then here. Can't draw that very well, but it's actually not too bad. And those, you might say, this horizontal, but no, it is vertical with respect to the principal axis. So these are sigma V's. The V stands for vertical. Again, I told you I'm going to come back. Let's look at principal axes first and see if we can find them for different molecules. So let's take a look at these 6 here. And so stop and build it if you want, right? The first ones are all tetrahedrals. That's important. So I have this build here. This is methane, the first one here. You actually have a few different symmetry elements here, but just looking at the axes of rotation. If you look down one of the carbon-hydrogen bonds, you can see there's a 3-fold axis here. So that's a C3, okay? So you can rotate that by 120 degrees, and you would have 3 of these C3s. There would be 1 through every single one of these axes. So that's important too, that you know. Sometimes you will be asked to find how many there are. So in this case we have 3. Now this is all cluttered up and harder to see now, but I could also just draw it like this on a piece of paper when I quiz you, and then you have to basically know, okay, these are not 90-degree angles, these is tetrahedron, 109.5, right? You have to apply the knowledge that you have about Vesper theory, and you've got 2 semesters of organics, so you shouldn't have any trouble. But there are also 2-fold axes, and so for the 2-fold axes, you're looking right down on it, okay? So if I put an axis through the carbon, but not through the hydrogen-carbon bond, in between, through this carbon, I have a 2-fold axis, which means I can rotate that 180 degrees and project it into itself. All right? So I'm going to put it and hold it towards you. So now the axis goes through the carbon and through my nose, and when I rotate that by 180 degrees, it gets projected into itself. Now this may be good, but at some point you really do want to build these. So we have C2s and we have C3s, but we have nothing higher than a C3. That's the highest one. So that would be our principal axes. Now this one here, I've replaced 3 hydrogens with chlorines. So if I kind of magically switch the hydrogen out with a green atom, you have now destroyed all of the C2s. All of the C2s are gone, right? So if you do a C2 here, that green atom is going to project into a white one, right? So whether this is hydrogen or chlorine or whatever it is. So that doesn't work. In our case, the green one is supposed to be the hydrogen and the white ones are the chlorines. So, but it doesn't matter. We have 3 of the same atom and then 1. But the C3 is still there, except I only have 1. Okay, so I've killed 3 of the C3s, and I only have 1 left over. So by replacing, I mean, technically I could have just replaced 1 hydrogen with the chlorine, replaced 1 atom, and arrived at that same symmetry. And so that means that I've destroyed quite a bit of symmetry. I took a bunch of the C2s out, all of them, and then all I have left is the C3. If we magically replace this one here with a green atom, okay, now we no longer have a C2. Sorry, C3. The C3 is gone now. Green would rotate into white, or hydrogen into chlorine if you want to be more chemical. But we have a C2 gained back now, right? So there's a C2 between the 2 green chlorines or bromines and the hydrogens here. So that's still there. Okay? So here we have a C3 is our principal axis, and here we have a C2. But we're down to just a single one. So this is like very symmetrical here, methane, right? Perfect tetrahedron, all of the angles are the same. And so just replacing 1 or 2 of the atoms really can make something more interesting or less symmetrical. Okay, so moving on to this molecule here, we're all familiar with it. This is benzene, and you should understand that this is not cyclohexatriene, right? It is benzene, so the reality is that we have a flat hexagonal disk, and all of the carbon-carbon bonds have the same bond distance. These hydrogens that are on here are in the plane, so we definitely have a mirror plane here, at least in the plane of the molecule. And so you need to remember that if I draw something like this, its 3-dimensional shape might be different from what it looks like on a 2-dimensional surface. So we now look for symmetry, right? And so we actually have C2s. We got a whole bunch of them. You can put a C2 through here, okay? And so through all of the carbon-carbon bonds, but also through the carbons themselves, okay? So those are all C2s. All right. So do we have something higher than that? And I mean, we have a perfect hexagonal disk, so it would make sense that we probably have a 6-fold axis, and we sure do. Through the center, if you rotate it around that axis, which goes straight up and down the board by 60 degrees, which would be a C6, this carbon rotates into that carbon, and so on and so forth. But we also have a C3, exactly where this axis is, because we can also do a 120-degree rotation and still end up here in the same position. Oops, I meant to draw through these 3 carbons here, so you can see that there's the C3, and so those will have the same position. And so this one here shows you nicely where the C2s are and where the C6 is. It's a little bit better, and yeah, didn't even think about it. There's a C2 as well, because you can do a 180-degree rotation and rotate this carbon into that carbon. So that's also there. And here all of the, not all, yeah, all of the C2s, but some of the C2s are shown here, most of them. Anyway, before I come back to this, I think that's all. It's enough for now. I'm over my 15-minute limit. So I'm going to do the next 2 when we come back, and then go straight to the sigma B's and sigma H's.